In this video, we are going to go over how to program the fourth order Runge Kutta method for the example that I just went over in the module. Runge Kutta, or this Runge Kutta method, is called fourth order because the error is h2 of the order h to the fourth. So as h gets smaller, our error gets smaller. Just for comparison, the error in our Euler method is h squared. So this method is more precise, or exact rather, than our Euler method, which is why we use Runge Kutta methods. So I've gone ahead and written a clear, close all, and CLC, and that's just so I start with a fresh slate in case maybe I had something in my code that was incorrect before, and I just want to run it each time so that I start with a fresh slate. Here I have f is equal to, and it's an anonymous function, and here I have two input variables, both t and y, and I have y minus t squared plus 1. My step size is 0.5. I've created a t vector that goes from 0 to 2 with a step size of h, and I've put in my initial condition y1 is equal to 0.5. Now, when we use numerical methods to solve our differential equations, we most always have to put a for loop. Almost always we have to use a for loop. It's pretty much, we're not able to vectorize our differential equations the way that we are integrals and derivatives. So I'm going to start with a for loop. I'm going to go for I equals 1 to the length of t minus 1. And no, I'm going to the length of t minus 1 because I'm always calculating what's happening at the I plus 1 value, and I want my final y to be the same length as t. So if I'm calculating at the I plus 1 value, then minus 1, I'll end up being the length of t. I'm going to calculate k1 is equal to h times, we have f, and f is evaluated at t of I, y of I. For k2, we have h, and we once again have times f, but this time f is evaluated, instead of at t of I, it's t of I plus h divided by 2. And instead of y of I, we have y of I plus k1 divided by 2. Next, I have my k3 value. K3 is h times f, evaluated at t of I plus h divided by 2, and then y of I plus k3 divided by 2. Oh, sorry, k2 divided by 2. And lastly, I have k4, and that's going to be h times f evaluated at t of I plus h, and y of I plus k3. So if you want to see what f evaluated at these points looks like, look above in the module, and you'll be able to see what those calculations and what those equations look like. So once I have k1, k2, k3, and k4 calculated, I'm going to calculate yi plus 1. Note k1, k2, k3, k4, those values are going to change every loop, which is what I want to happen. So I want a new k1 for each loop that I have. So here I have y of I plus 1 is equal to y of I plus 1/6 times, and here I have k1 plus 2 times k2 plus 2 times k3 plus k4. and that should be my y value that I have calculated. Here I note my code is orange, and it's telling me that the variable y appears to change size on every loop iteration. If I wanted to get rid of that orange error, I would go up here and I would say before y1 is equal to 0.5, I'd say y is equal to zeros, and I want the number of rows of length of t and comma 1 column. So I'm just pre-allocating the space of y to speed up my code a little bit, and then I'm going to fill in each spot of y. Here I can plot by creating a figure. I'm going to have a hold on. My exact solution for this problem is equal to t plus 1 squared. So t is a vector, so I need this element-wise power minus 0.5 times the exponent of t. So that's the exact solution. This would be given to you in any lab, quiz, final, etc. that I would give you. I would give you that exact solution. So we're going to hold on, and then we're going to plot t comma y, and let's use circles in a solid line, and we're going to use color black. We'll do a line width of 2 just so we can see it better. And then we're going to plot t exact. Let's use red dots, but let's make them large. We're going to do a marker size of 15. If I run my code, I see that I get this plot right here, and it looks like my Runge Kutta method is really close to my exact method. I could add these lines of code right here to make my plot look a little bit better. So I'm adding a legend, a title, Y label, X label, and changing my font size. So this was an example using our fourth order Runge Kutta method to solve a differential equation.